Hello, good evening everyone. Am I audible?
Yes, ma'am.
Okay, thank you. Thank you. Also, my screen is visible, right?
Yes, ma'am. Visible, ma'am.
Okay. Okay, so uh, good evening everyone. I welcome you to the last week of the NPTL course Graph Theory. So today, today's topics are chromatic number, chromatic index, and the planar graph. So from last few, so these are the last topic from this course. Okay, so first of all, let's recall what are the whatever concepts that were discussed. Firstly, what is a k colorable graph? A k colorable by saying a graph is k colorable, we mean that we can color the vertices of graph with k colors with this one rule, that is if there are two adjacent vertices, they cannot have same color. So if if there is a edge between two vertices, those two vertices cannot have same color. And if we can do this by and for if we can color the vertices with k colors in such a manner, then we say that this graph, when given graph is a given graph is k colorable. Now, once we know what is k colorable, then there's this notion of chromatic number. So by chromatic number, we mean a least k for which the g is for which least k for which g is k colorable, and we denote it by xt. So so chromatic number is giving you the least number of colors required to color the vertices, such that no two adjacent vertices have a common color. So now we from all over this course we have discussed various examples. So let's try to see what will be the chromatic number of those examples. So first is a null graph. By null graph we mean a graph which has no edges. So this is a graph with no edges. Since there are no edges, we can color all the vertices by same color, say green. And the rule that is that no and since there are no edges and since there are no edges, so that rule is trivially satisfied. So we see that chromatic number of null graph will be 1. Now second is bipartite graphs. So we have seen bipartite graphs. So bipartite graphs are basically graphs, we have two independent sets, and within those two sets all the edges are between. So this is set A and this is set B. So all the edges go from A to B. There are no edges within A or within B. Therefore we can color all the vertices of A with one color and color the vertices of B with one color with some different colors. So we see that two colors are sufficient to color the vertices of bipartite graph. And now next common example was of a kn, which is a complete graph. So in a complete graph with n vertices, we have that all the vertices are attached to each other in a sense that there's an edge between any two distinct vertices. So now we have n vertices, and all the between any two vertices there's an edge. So all the vertices should have different color by that rule. Therefore we see that we can since there are n vertices, so the number of colors required are less than equal to n, but here it is exactly n, because we cannot color this graph. Chromatic number will be n because we cannot color this graph with n minus 1 colors, because there's a common edge between any two vertices. Now next example is of even cycles. So when we look at even cycles, so what should be the chromatic number of even cycles? So if we have even cycle, that means we have even number of vertices and we have a cycle. So there isn't one edge, but there. So basically, degree of each vertex is 2. So it's a cycle. So now for even cycle also we see that chromatic number will be 2, because we can color it alternatively. So vertices at odd positions can be given one color and vertices at even position can be given one color. And obviously we cannot so chromatic number is 2, so we can color this graph with two colors, but we cannot do this by one color. So chromatic number is 2. So now another common example is of odd cycle. So what do you think? So this is what do you think will be the chromatic number of a odd cycle?
3.
3.
3, ma'am.
3. So okay, first so why it will be 3? Can't we do it by two colors like previously?
We cannot do.
Yes, so see, if we, yes, we cannot do, because if we'll do it alternatively, in the end, so if we color all the odd vertices, say blue, and even vertices are green. So we did do this till 2n. Now when we look at the 2n plus 1 vertex, so all the, so see 2n, so this is a cycle, so this is a graph like this. Now we see for V2n plus 1, we cannot color it by green or blue. So we have to choose a different color, say red. So we see that we cannot color it by two colors. Therefore, chromatic number of an odd cycle will be 3. Now next example is of wheels. So first of all, this wheel have odd vertices. So basically we have a even cycle outside, and there is one vertex which is attached to each of the vertices in the cycle. So what will be the chromatic number of first graph, which is a wheel with odd vertices?
3, ma'am.
Okay. And how should we color it? So in what should how should we color it with three colors?
That center vertex with one color, ma'am.
Yes.
And the outer vertices should be alternatively colored with the two colors.
Yes, yes. So we see, so we have already seen. So see, so this is a graph which has a, this is a graph which has a which has a even cycle, and we know that if H is a subgraph of G, then the chromatic number of H will be less than equal to chromatic number of, sorry, yes, it will, chromatic number of H will be less than equal to chromatic number of G. So since it has an, or since it has an even cycle, we know at least we need two colors, and let's do it. So as previously we color the alternate vertices, but now, okay, sorry, but now we have also another additional vertex which is attached to all the vertices. So we cannot give them color either of blue or purple. So we'll have to give it a some different color, which is green. So we see that chromatic number of this will be 3. And what will be the chromatic number of wheel with even vertices? So we have an odd cycle outside, and then there's we have an odd cycle outside, and then we have a vertex in middle which is connected to all the other vertices. So by same logic, what will be the chromatic number for this wheel?
4.
4, ma'am.
4. Yes. So because the outer cycle will require 3 colors, by the same argument, outer cycle will require 3 colors, and then we'll have, and a middle vertex will require the fourth color. So we see that we need 4 colors for this. Now these were the general examples. Now we also have some bounds on chromatic numbers. So let's discuss. So first bound is due to click. Now, so first, what is a click? Click is basically any complete subgraph of G is referred to as click. Uh, so like in this example we see that these three vertices, and there's, if we look at these three vertices, all the vertices are attached by there's between any two distinct vertices there's an edge. So we see there's a K3. So this is a K3. So this is also, so any complete subgraph of G is referred as click, and omega G is omega G is used to denote the size of largest click, and we can size of largest click, and so the chromatic number of G will always be greater than equal to the size of largest click, because if the size of largest click is say K, that size of largest click is say n, then that means Kn is a subgraph of G. And previously in examples we have seen that chromatic number of Kn chromatic number of Kn is n. Therefore, we see that chromatic number of G will be greater than equal to n. So this is the first lower bound on the chromatic number. Then there's another there's a lower there's a upper bound also on chromatic number. It is that which is that chromatic number will always be less than equal to the degree maximum degree plus 1. So del G here refers to maximum degree, which means that if we look at the degree of each of the vertex and take the maximum of it. So chromatic number will always be less than equal to this, and this can be shown if we try using, we can color any graph by greedy algorithm. So this can be shown using that. And so interestingly this bound we also have another, oh sorry, we also know when this we also have a necessary and sufficient condition for the for graphs when they achieve this bound. So we have that chromatic number of G, this will be it will be equal to maximum degree plus 1 if and only if G is either a complete graph or G is either an odd cycle. So in our previous example we have seen that for Kn is a regular graph which has maximum degree n minus 1, but we have seen that chromatic number of Kn is coming out to be n. So we see that for Kn chromatic number is equal to maximum degree plus 1. And similarly for odd cycle also, since the degree of each vertex is 2, maximum degree is 2, but we need at least 3 colors to color any odd cycle. So for complete graph and odd cycle, this bound is attained. But the interesting thing is that only this is if this bound is attained only for these graphs. So we have seen one way around, but the converse is also true, that if chromatic number is equal to maximum degree plus 1, then G will be either a complete graph or an odd cycle. Or in other words, we can say this can be restated in this manner, that if G is not a complete graph or if G is not an odd cycle, then chromatic number will always be less than equal to the maximum degree of the graph. So is the last statement clear to everybody?
Yes, ma'am.
Okay. Okay, so so the first part of today's was vertex coloring. So now we also have we have a analogous topic of edge coloring. So similar as we have defined what was vertex coloring. So we were coloring vertices, and no two common vertices should have same color. So what is edge coloring? Now instead of coloring vertices, we are coloring edges, and the condition is that if two edges share a common vertex, then they should not have a same color. So K edge coloring. So basically a graph will be called K edge colorable if we can color its edges by K color in such a manner that no two edges with common vertex have same color. And the least K for which the graph G is K edge colorable is known as chromatic index. So psi G was chromatic number. This was referring to the least number of colors required to color the vertices. And xi dash G is the chromatic index. So which is the least number of colors required to color the edges. So please note this distinction. For vertices it is chromatic number, and for edges it is chromatic index. Now as we had some bounds on chromatic number, there are some nice bounds. There are some even nice bounds on chromatic index. So we have this, that chromatic index will always be less than equal to maximum degree plus 1, and it will also be always greater than equal to maximum degree. So if we combine these two things, we'll get that there are only two possibilities for the chromatic index. it can either be equal to the maximum degree, or it can either be equal to maximum degree plus 1. So this is very different from the chromatic number. For chromatic number we have various possibilities. For chromatic number we just have that it should be less than equal to maximum degree plus 1, and all types of things can be attained. But for chromatic index we have just two possibilities. It can either be equal to the maximum degree, or it can be equal to maximum degree plus 1. and and using these two things, the graphs can also be divided into two categories. First type is class 1 graphs, that is for the graphs for which the chromatic index equals the maximum degree, and the second class of graphs is the graphs whose chromatic index is maximum degree plus 1. and and so this was a theorem in class that bipartite graph is a class 1 graph, that for bipartite graphs the chromatic index always equals the maximum degree. and and for even cycles also, we can see, in particular for even cycles also we can see that the chromatic, so even cycle is also a bipartite graph. So it is just a particular case of bipartite graphs. And some examples of class, if we want to look at some example of class 2 graphs, so all the regular graphs of odd order, will be class 2 graphs. That is, for regular graphs of odd order, chromatic index will be maximum degree plus 1. So if you are given a regular graph for odd order, you can directly say that the chromatic index is maximum degree plus 1. uh, and particular examples of regular graphs of odd order will be are odd cycles, or complete graph with odd number of vertices. So this was what was chromatic number and chromatic index. Now let's compute some chromatic number and index for some examples. So first question is taken from the assignment. So this is, so we see that yeah, so we have this, that chromatic number will always be less than equal to the maximum degree plus 1, and chromatic index has only two possibility. It is either maximum degree or maximum degree plus 1. So in this particular graph, what is the maximum degree of the graph? What is the maximum degree?
4.
4.
4.
4.
4. Yes. So the maximum degree of this graph is 4. So we know, first of all, if you want to compute the chromatic number, so what will be the chromatic number for this graph?
4.
4. Okay. Why it will be 4?
We need 4 colors to
Yeah.
to give the vertices.
Yes. So yeah, so you're right, we need at least 4 colors. So we can see this, so we need at least 4 colors to color these vertices. So first of all, we can observe that, so if we observe these vertices 1, 4, 3 and 2. So 1, 4, 3 and 2, this, if we observe these 4 vertices, just these 4 vertices, we see that this is a complete subgraph of G. So K4 sits inside this G. So we know that chromatic number of this graph is less than equal to 5. But since K4 is sitting inside G, we also know that chromatic number is greater than equal to 4. So we see there are only, for chromatic number also we have just two possibility. It can be either 4 or 5. But if we want to color it with just 4 colors, so first of all, these 4 vertices will have distinct color, because it is a complete graph. So we give some 4 distinct color to these 4 vertices. Now we want to look at the color for the 5th vertex. So now this 5th vertex Fifth vertex. So fifth vertex is already attached to vertex with color black, pink and blue, but it is not attached to the vertex with color green. So we can color this vertex as color this vertex as blue. So we see that this chromatic, so we see that we are able to color this graph with four colors, color the vertices of this graph with four color, and we know we need at least four color, therefore chromatic number is indeed 4. But what about, now the next question is, what is the chromatic index? Is the chromatic index 4 or 5? So there are only two possibility for chromatic index for this graph. It will be either 4 or 5. So what is the chromatic index for this graph? What do you think? So in chromatic index, we need to color the vertices. We need to color the edges. Okay, so let's try to let's see what can we do. Let's try to color the edges. So let's first pick up the color red. Now suppose I am coloring my 1 2 edge with red. So now I cannot color, any other edge, which is attached to 2 or 1. So I pick some other with color red, I pick some other edge which is not attached to either 1 or 2, 4 and 5. So I have picked some other edge 4 5. So now with this red color, can I color some any other edge? So if I have used if I use my this pink color to color these two edges, can I color this graph with can I use this color pink to color any other edge of this graph?
No.
No, ma'am, no.
No, ma'am.
No. Okay. Why?
Because
If we color, then there will be a common vertex, ma'am.
There will be a common vertex.
Common
So
vertex.
we observe that any color any color can be used here, can be used for at most two edges. So everyone, so this was some pink color. This, since this graph has five vertices, with one color we can only color two edges, right? Because if we color two edges, we have picked four vertices, and if we have to color some other edge, we'll have to repeat a vertex. So any color can be used for at most two edges. Any one color can be used for at most two edges. And how many edges are there in this graph? How many? Sorry. How many edges are there in this graph?
8,
5, 6, 9.
9.
9. There are 9
9.
edges. So what do you think? How many colors do we need? So there are 9 edges. So we have already observed that one color can be used for at most two edges.
5, 5.
So we need
Five.
we need at least 5 color. So we know that chromatic index is either 4 or 5. But now do we know why we cannot use 4 colors to color this graph? Four colors to color the edges of this graph. Now is everyone convinced? Because if we can due to this observation, 4 colors can color at most 8 edges, but this graph has 9 edges, so we'll need a fifth color. Therefore chromatic index of this graph will be 5. So any doubts in the first question?
No, ma'am.
Yeah, also, yeah, okay, and we can see, so we can basically, yes, so color it by 5 colors. So now since I have used 1 5, now I have to use take some edge which is not using either of this, and so we can see that we'll be able to color it with 5 colors. Okay, so now next question. What about this graph? What do you think is the so here also what is, first of all, what is the maximum degree of this graph?
3.
Yes, maximum degree of this graph is 3.
3.
Maximum degree is 3. Now chromatic number we know should be less than equal to 4, or it should be, since this is neither since this is neither a complete graph nor an odd cycle, so we can say that chromatic number should be less than equal to 3 using the second lemma, using the second up bound, because we know that a chromatic number is always less than equal to maximum degree plus 1, but this case can happen only for complete graphs or odd cycle, but this graph is neither complete nor an odd cycle, so we know that chromatic number will be less than equal to 3. So what do you think? Can we color this? So chromatic number is less than equal to 3. So we have to see first that, so chromatic number is less than equal to 3. That means we can color this graph with 3 colors. Color the vertices of this graph with 3 colors. But can we color the vertices of this graph with 2 colors?
No, ma'am.
Why? Why? Yeah.
Because it is an odd vertex.
Yes, because it has an odd cycle. So we have an odd cycle, and for an odd cycle we need at least 3 colors, right? So chromatic number will turn out to be 3. So also now if we want to color it with 3 colors, can you give me a coloring of this graph? Like we have 3 colors, blue, green and red. So chromatic number is coming out to be 3. Then we should be able to color this graph with 3 colors. So what should be the color? So if I am giving, yeah. So if I am giving,
1 and 3 with blue, 2
okay,
and 5 with green, and 4 with pink.
okay. So 2 and 5 with same color and 4 with blue. Oh, sorry. Yeah. So we see that this is the color. So so no, there is no common word, there isn't edge here, there's not a edge here, so we see that it is indeed there. Now so we have seen that chromatic number for this graph will be 3, but what about the chromatic index? What about chromatic index? Can we use a argument like previous, can we use something similar argument like the previous question? What will be the chromatic index? Chromatic index will also be 3
Delta
or
G
4.
3 or 4. 3 or 4.
4, ma'am.
4. Because how many edges do we have? Uh, we have 7 edges.
7
7.
edges.
7.
Okay, so we have 7 edges. Yes, we
One,
have 7 edges. So we,
one color for 2 edges.
one color for 2 edges. So we need
So
at least,
there will be 4 4
we
colors
need
will
at
be
least 4 colors. Yes,
4 colors will be required.
yes. So we see that chromatic index will also be 4. And if we want to color it, so basically if I'm giving purple, so these will be the 4 colors. So these will be the 4 colors. Yes. So these will be the 4. Yeah.
And can you repeat that about the chromatic number is equal to delta G plus 1? It is for complete graph and
Odd
graph
cycles.
having,
Odd cycles.
graph having odd cycle.
If G is a complete graph or an odd cycle,
Okay.
then the chromatic number will be so I said that chromatic number will be equal to maximum degree plus 1 if and only if G is an odd cycle. G is either an odd cycle, that is G is
Complete.
either C2n plus 1 or G is Kn. Only for these two possibility, only for these two graphs we have that chromatic number will actually attain this bound. That is maximum degree plus 1. Other than these two graphs, chromatic number will always be less than equal to the maximum degree. Is it fine? Okay.
Ma'am, edge 3-4 color, ma'am.
Sorry?
The color for edge 3, 4.
Will be just black. Black.
Okay, ma'am. Okay.
Yeah. Yeah. Okay. Now, next. So what is, so now this is from your practice problems. What is the uh okay. So what is the maximum degree of this graph?
3.
Hmm.
3.
It's 3. Yes, it is 3. So chromatic number is less than equal to 3. So we can this graph is also not a complete this graph is also neither a complete graph nor an odd cycle. So from that bound, first we have that we can say that chromatic number will be less than equal to 3. But this graph has so what will be the chromatic number for this graph? So
And
from
this graph has odd cycle, I think.
yes, we have 9 vertices. It has an odd cycle. Yes.
Hmm.
Yes.
The execute with the
So
3
we
plus 1. No?
no, I'm no. So
It is odd cycle.
it but it is so the
Oh,
condition is that G is equal to
sorry,
an
sorry.
odd cycle. It is not that G has an odd cycle. So this so xg,
It has 10 vertices.
yes, there are 10 vertices. Yeah. So yeah. So the first of all, that doubt, xg is equal to maximum degree plus 1 if and only if G is equal to C2n plus 1 or G is equal to Kn. So we are saying that G is a G is an odd cycle. We are not saying that G has an odd cycle. If G has an odd cycle, then we can, if G has an odd cycle but G is not then we cannot say that it will be less than equal to it will be equal to 4. This bound is only attained when G is a graph which is exactly that odd cycle. There are no more edges other than that. But this graph has an odd cycle, but graph is not an odd cycle. So therefore we'll say that the therefore chromatic index will not be equal to 4 and it will be less than equal to 3. Is it okay? Now we have to see what will be the chromatic number. So we have first noted that chromatic number will be less than equal to 3. So what is the chromatic number for this?
4, ma'am.
uh no, chromatic number for this is less than equal to 3. It cannot be 4. Chromatic number is equal to maximum degree plus 1 if and only if G is a complete cycle. So this graph is not a this sorry this if G is a odd cycle, this graph is not an odd cycle. So by C2n we just so if we had just these 9 vertices and if we just had this 9 vertices and that just odd cycle, then the chromatic number will be then the chromatic number will be equal to maximum degree plus 1. But this graph is not satisfying any of this hypothesis. This is neither a complete graph and it is neither a odd cycle. This graph is not an odd cycle. It just has one odd cycle. But this condition is different from saying that G is an odd cycle. Is that clear?
Yes, ma'am.
Is the confusion clear? But when we are saying that G is equal to C2n plus 1, we are saying that there is just one odd cycle. The graph is just the cycle. There are no more edges than that cycle. But this graph has a C9. But this is not equal. This graph, the present graph, has a C9, but it is not equal to C9 because it has many more edges and many more vertices other than C9. Right?
Hmm.
So now, so it cannot be 4. It cannot be 4 because we know that if G is not a complete graph, or if G is not an odd cycle, then the chromatic number is less than equal to the maximum degree. And maximum degree of this graph is 3. Therefore, chromatic number has to be less than equal to 3. So it is either 1, 2 or 3. So what do you think? What is the chromatic number for this graph?
Uh,
Can it be, so we have
Three.
to, we this,
Three.
can it be 2?
One.
Can we use two colors?
Oh,
Can we use two colors to color this graph, color the vertices of this graph?
yes.
Are two colors sufficient to color the vertices of this graph?
No, ma'am. I
If we,
think four. I
if
think.
we color
Three
center,
colors, ma'am.
Three colors,
if we
yes.
color center one with say red.
See, this graph has an odd cycle. And we know that chromatic, so if this graph, so if we start coloring the vertices of this cycle, we know that since it has an odd
Four.
cycle, we need at least 3 colors. We need at least 3 colors, right?
Yes.
We need at least 3 colors to color this graph, because so now this, and since the chromatic number is less than equal to 3, chromatic number will be exactly 3. So without even coloring this graph, we can conclude that chromatic number is 3 using our previous result. Since this graph is neither an odd cycle nor a complete graph, we know that chromatic number will be less than equal to 3, and chromatic number of this graph cannot be equal to 2, because it has an odd, because for coloring these 9 vertices we need at least 3 colors. We cannot color first 9 vertices with 2 colors. So we know that this chromatic number cannot be 2. So the only possibility left for this chromatic number is 3. Therefore, without even doing any coloring, we can directly conclude that this chromatic number is 3. Is that clear? How? Without even.
Yes, ma'am.
So now we know that chromatic number is 3. Now,
What,
na-
what
yes,
about center of the center vertex?
yes, yeah. So now we'll look at, now we have, so now from our results, from our theorem, we know that chromatic number is 3. From our theorem, we know that chromatic number is 3. Now we have to find the specific coloring with 3 colors. So let's find it. So first of all, we are coloring these odd cycles. Let's say, uh, so sorry. So we know we need at least 3 colors. So let's try to color this graph with 3 colors. So first I am coloring this with green, blue. Now, okay, sorry. So let's try to color this graph with, let's try to color the vertices of graph with 4 color. So first I'm coloring this with green, then blue, and I can give color blue to this one, and now blue to this. I cannot give blue to this because there is an edge here. So I have to give it the third color. I cannot give color blue to the vertex 6 because it already has a, it already has a, it already has a vertex, it already has a vertex with adjacent vertex with green color and blue color. So I have to give it the third color. Now similarly for this, now since this has green, I'll okay. So I can give this blue. I can give this pink because it already had green and blue. And I can also give this pink, and I can give this blue. So we have colored this graph with 3 colors, and we can see no two vertices which are same color have a common edge. Is it clear? So first, by using our theorems, we can directly conclude that the chromatic number should be 3. Then we gave a specific color. Then we gave a specific coloring also. So is this question clear to everyone?
Yes, ma'am.
Okay. Also, so I sensed some confusion regarding this theorem also. So is the confusion regarding this theorem clear to everybody, or should I repeat again this theorem? This statement is this statement of this theorem clear?
Hmm.
So so when we are saying G is equal to C2n plus 1, we are not saying that G has an odd cycle. We are saying that G is exactly that odd cycle. Like in this example, we see this example, G is not an odd cycle. G just has an odd cycle. So that is the distinction. So we cannot use this theorem for this. We cannot use the theorem in the box for this graph, because this graph is not complete, and this graph is also not an odd cycle. Okay. Now if this is clear, let's move to next question. Okay. So now the next question is, what is the chromatic index for complete bipartite graph? So first of all, if G is a bipartite graph, do we have any theorem which which if G is a bipartite graph, do we know whether this graph is a class 1 graph or a class 2 graph?
Class 1 graph.
Class 1.
Class 1 graph, yes. So we know that complete bipartite graph is a bipartite graph, so we know that from that theorem that it is a class 1 graph. So chromatic index for this graph will be the maximum degree. So what is the maximum degree of complete bipartite graph? So what is the maximum degree of complete bipartite graph? So by complete bipartite graph, we means that, so set A has m vertices, v1, v2, vm. Set B has n vertices, w1, w2, and wn. And all the vertices of A have an edge with the vertices of B, and vice. All the vertices of A has an edge with vertices of B, and all the vertices of B has an edge with all the vertices of A. So if we see K32, it looks like something like this. K32 is this. So now if this is the set A and this is the set B, so what do you think is what is the degree of each Vi? Vi is belonging to A. So what is the degree of each Vi? A has m
N.
vertices, B has n vertices. Degree of each Vi is
N.
n. And what is the degree of each Wi?
Same. N.
M. So what is the maximum degree? What is the maximum degree?
M plus N.
N.
No. Maximum degree of this graph. So
Maximum of 2. Maximum of 2.
maximum of m or n, right?
M or here. M or N.
So from the theorem we know that if G is a bipartite graph, chromatic index should come out to be equal to the maximum degree. Now in complete bipartite graph, we have two type of vertices, set A and set B. And all the vertices in A have degree n, and all the vertices in B have degree m. So what is the maximum degree of the graph? It is maximum of
Maximum of M
m
and
a
N.
n. And therefore, using this theorem, we can conclude that chromatic index of complete bipartite graph will be maximum of m n. So for K32, what is the chromatic index?
3.
3.
3.
3. Yes. For X chromatic index for, and similarly we can, now we know the chromatic index for any complete bipartite graph. Okay. Next question. So now the next question is that G is a 3 regular Hamiltonian graph. Hamiltonian graph. That means degree of each vertex in G is 3. Now we have to find the chromatic index. So we know that chromatic index is less than equal to maximum degree. Sorry, chromatic index is equal to either maximum degree or maximum degree plus 1. Del G or del G plus 1. And since this is a 3 regular graph, the maximum degree is 3. So we know it will be either 3 or 4. So now we have to show, now we have to say, now if we can color this graph, with, if we can color the edges of this graph with 3 colors, then we can say that chromatic index will be 3. So let's see if we can do that. So first of all, if G is a Hamiltonian graph, what do we mean by a Hamiltonian graph? What is an Hamiltonian graph? Yes. Yes.
Graph with the
Semi-Hamiltonian
Hamiltonian
cycle.
cycle.
Yes, graph with graph with a Hamiltonian, so graph with a Hamiltonian cycle. Yes. Also, if this graph, if the degree of each vertex is 3, can we say anything about the number of vertices? Can we say that number of vertices will be even or odd?
Odd. Odd.
Degree of each vertex is 3. So now why
And
number of
more
vertices will be odd?
because
Even,
degree is
ma'am.
2, no?
Even. Yes. Why will it be even?
The number of degrees always less than the number of vertices.
Number of degree
Is less than minus 1 the number of vertices, ma'am.
Oh, that is not true. Number of what?
Number of odd vertices
N
will be
minus 1,
even.
ma'am.
Yeah, okay. Yes, that is fine. That
Number of
number
degrees
of,
of vertex.
yes, that is fine. That degree of vertex, if we are in a simple graph, degree of vertex will always be less than equal to number of vertices minus 1. That is fine. But now we want to say that each vertex has degree 3. But the claim is that number of vertices will be even. So from how can we conclude this from this? So why can we say that number of vertices will be even?
Number of degree of all vertices is equal to 2 into number of edges.
Yes, that is right. Because sum of degree of all vertices is always even. So from this we can conclude that number of odd vertices will be even. And since all the vertices are odd here, so we see that this graph will have even number of vertices. So we now have a and we know that this is a Hamiltonian cycle. So if this is an this is a Hamiltonian graph. So we have some even number of vertices. We have some even number of vertices. And then we also, and it is 3 regular. So first of all, we have an Hamiltonian cycle. So we can color this cycle. Color this cycle with 2 colors. Alternate colors. So we can color this Hamiltonian cycle with 2 colors. So color the Hamiltonian cycle with 2 colors. So we have used our 2 colors. Now if we look at, so suppose if we look at the graph, so this is a 3 regular graph with a Hamiltonian cycle. Now if we remove the Hamiltonian cycle, so so how much degree to each vertex is this Hamiltonian cycle contributing?
2,
2. But this so if we remove this
but it is
if we remove this, if we remove this Hamiltonian cycle, in the remaining G minus H is a, we can see that it is a 1 regular graph, because this Hamiltonian cycle is contributing degree 2 to each vertex, but given graph is 3 regular. So the remaining graph will be 1 regular. And what is a 1 regular graph with even vertices? What is the only possibility of 1 regular graph with even vertices? So basically we have 2n vertices. Suppose we have 6 vertices for say, and the graph is 1 regular. That means degree of each vertex is is 1. So this is the only possible bipartite graph of some this type is the only possibility. So we'll have some we'll have a we'll have the remaining graph will be of type this. So we can use our third color to color the rest of the edges, which is this. And since the only so we can see that if we use one and since these edges are not intersecting, we can use the same color for all the remaining edges. Use the third color to color the remaining edges. So we, in short, in conclusion, we have colored this color and a Hamiltonian graph which was a 3 regular. We are able to color this Hamiltonian graph with 3
Okay.
colors. Therefore we see, and we knew that the chromatic index chromatic index is either 3 or 4, but since we are able to do it with 3 color, so we can conclude that chromatic index is indeed 3. So is this question clear to everyone? Any doubts in this question?
Mm,
once.
Oh, okay. I'll repeat it again. Yeah.
Why it is 3?
Sorry. Yes. What are you saying? Sorry, I didn't hear.
And can we
Oh,
regular this find it for K regular Hamiltonian?
Can we?
If it is, can we
Sorry.
generalize this with K regular Hamiltonian graph?
Uh. Uh. Oh, sorry. Wait. What is this?
Can we
Ge- I
generalize it?
uh, okay, I don't think we can generalize it. Suppose even if we, because so see, if it the we were able to do this, because it was 3 regulars. So first we used our 2 colors to color these 2 colors. But when we'll remove this Hamiltonian cycle, so if suppose if we have this K color, suppose if we have this,
Hmm.
first of all, if this k is not odd, suppose if this k is not odd,
Hmm.
suppose even if we want to generalize it first for the k odd, Okay, I'll come back to generalization. First of all, somebody wanted to repeat this proof. So if I if, so what was your doubt in in this particular example? Then we will look at the then we'll see if we can look at the generalization or not. I think somebody asked.
Ma'am, how
Yeah.
we conclude that it was exactly 3?
Yes, how do we conclude that it is exactly 3? Okay, so see, we know that chromatic index is either equal to the maximum degree or maximum degree plus 1. And chromatic index is the least number of, it is basically the least number of colors required to color the edges. And you, by this procedure, so from first of all, from this theorem we know that it will be either 3 or 4. And from this procedure we were able to color this Hamiltonian graph, Hamiltonian 3 regular Hamiltonian graph with 3 colors. So, we know we need at least 3 colors, and we are able to color it with 3 colors. So 3 is the least number. Hence the chromatic index will be 3. We so it is either 3 or 4, but since we are able to color it with 3 colors, it will be 3, because we are looking for the least number of colors required to color the edges of this graph. So from this we know it should be greater than equal to 3, but we are able to color this with 3 colors, therefore 3 is the least number. Is it clear now?
Yes, ma'am. Yes, ma'am. Yes.
Okay. Now if we want, now the question is if we can generalize this. So there is no direct generalization, like maybe we can, but using this method we cannot generalize. Suppose this graph was 5 regular, say 5 regular Hamiltonian graph, and if we apply the same procedure, we'll know that this graph will have even number of vertices. So first we use two colors. First we use two colors to color the Hamiltonian cycle, like before. But now if we remove this Hamiltonian cycle, since so it is a 5 regular graph. Now if after removing the Hamiltonian graph, it becomes a 3 regular graph. So it becomes after removing it, it becomes a 3 regular graph. So, okay, if it is becoming a 3 regular graph, okay, yeah, if it is becoming a 3 regular graph, then we cannot directly conclude that we will need, so it is a 5 regular graph, so we know that it will be the maximum degree will be either 5 or 6. Now first we use two colors to color our Hamiltonian cycle, say this. So now if we are using this, now the remaining graph is becoming a 3 regular graph, but it has even number of vertices, and it is a 3 regular graph. Suppose, so we know that it is 3 regular, then chromatic index of G minus, for G minus H also we will need uh, chromatic index for this will be either 3 or 4. It will be either 3 or 4, but we cannot directly say whether it will be 3 or 4, because it is a 3 regular graph and it has even number of vertices. Even if it has odd number of vertices, then maybe we could have said something. So I don't think there is any direct generalization for this case. Like if we can generalize, like I don't see it right now. But for 3 regular graph, we can say that it is coming out to be 3. You, at least using this same method, we cannot directly we cannot conclude if the if we can generalize this. Maybe there's some other method. Okay, is this fine then? uh, is okay. Now let's move to next question. Okay, so
And how to solve if the question is asked for
yes,
five regular Hamiltonian graph,
yeah,
what is the chromatic index? Then
yes.
how to solve that? How to solve that?
Oh, so see, if it is a five regular, so maybe if it is, so there might not be an answer also, right? So so if it is a five regular Hamiltonian graph, it might be possible. So for this we can say it will always be 3, but for this, like for this, I have no direct thing. So maybe there are some five regular Hamiltonian graph whose chromatic index will come out to be 5, or and some five regular Hamiltonian graph whose chromatic index will come out to be 6. So it might not be it might not be a valid question also, because if for some example it is coming out to be 5 and for some example it is coming out to be 6, then we cannot show it, right?
But the answer will be either 5 or 6. No,
Ah, yes,
answer will be
it will
either
be either 5 or 6, but
exact.
but 5 regular Hamiltonian graph is not unique, right? So there can be there can be a graph G which is also 5 regular Hamiltonian, and there can be a graph G prime which is also 5 regular Hamiltonian, but this one has this one has some different chromatic index, and this one has some different chromatic index. So maybe this cannot be generalized. So if this cannot be generalized, then it won't be a question. Okay, I'll see if I can find if I can find some either some examples, or if I can prove it. If I'm able to do it, I'll let you know. But right now, I can't see any direct method. Okay. Now this was about chromatic number and chromatic index. Now the last topic was of the planar graphs. So what are planar graphs? Planar graphs. Is there any question? So planar graphs are basically graphs which can be drawn so that no two edges intersect. So if we can draw these graphs in a plane such that there are no intersect no two edges are passing like this. That is, they are intersecting this edges. Then we say that this graph then that graph is planar. So we see that if we look at K4, this particular representation of K4, in this particular representation of K4, these two edges these two edges are intersecting. But since these two edges are intersecting, we cannot say that this graph is not planar, because we can draw this graph like this, in which no two edges are intersecting. Therefore, K4 is indeed planar. So by a planar graph we mean that if we can so if may, for planar graph it may be possible that some drawing of it is intersecting in edges, but if we can even find one drawing of that graph, one isomorphic copy of that graph, one isomorphic class of that graph in which no two edges are intersecting, then we say that that graph is planar. And we also have a nice formula for these planar graphs. That is, we have a nice relation between vertices, edges and faces. So what do we mean by, so we know what are vertices, what are edges. Faces are basically the area bounded by the edges. So in this square we have two faces, the inward face and the outward face. So These are the faces. So, so when we are counting faces, always remember to count the outward also. And in the K4, how many faces are there? 1, 2, 3, 4. So these are the faces. And for planar graph, we have this we have this nice relation that number of vertices minus number of edges plus what number of faces will always be equal to 2. This will be true for planar graphs. Now, we had a notion of degree of a vertex. Similarly, there is also a notion of a degree of face. So, what do we mean by degree of face? Degree of face is just the length of walk around boundary of any face. So, that is what is a degree of face. So, we can see, so in this diagram, we have 4 faces. 1, 2, 3. 4 faces. And what is the degree of each face? So the first 2 and 3 faces are triangles. So we see that if you want to walk around the boundary, we need, if you want to walk around the boundary, we need to take 3 steps. Therefore, degree of each face is 3 for F1, F2, F3. But for F4, the degree of each face, for F4 degree of face will be 5, because if we want to go around the outward face, so how we will go? We'll go BA, so we'll go BA, AD, DE, AD, DE, then ED, then DB, and B A A D D E D B and sorry A D E D D E. So we see that it will be 5. So why I'm getting B A A D D E E D D B. Yes, then DB. So we see that degree of F4 is 5. We started with B and we have come back to B again. So degree of F4 is 5, and we also have that sum of all degree of faces will be 2 will be equal to 2 number of edges multiplied by 2, and it has the same logic. So each edge, we see that each edge basically separates 2 faces. So we have 2 faces for each edge. Therefore one edge is one edge is counting for 2 faces, and this DE is counted for fourth face twice. So we see that sum of degree of each faces is always even, and it is equal to 2 times the number of edges. And now we have some relations between faces, edges and vertices of planar graph. So we had this first relation that was the Euler formula, which was V minus E plus F equal to 2. Now if our planar graph is simple, then we can see that degree of each face will be greater than equal to 3, because we cannot have any face, since it is a simple graph. Face of this type is not allowed, because this is a loop. So we see that degree of each face in a simple planar graph will be greater than equal to 3, which will give us this relation, that 2 times edges is always greater than equal to 3f. And once we put this relation in our Euler formula, we'll get this relation, that the number of edges is always less than equal to 3v minus 6. And similarly, so this is the first relation for the planar graph, that the number of edges is always less than equal to 3 times number of vertices minus 6. And moreover, if G has no triangles, then we can also conclude that number of edges will be less than equal to 2b minus 4. And we do the similar thing. Since G has no triangles, then we'll know that degree of each face will be greater than equal to 4. And we use the similar calculations to find this. And using these two inequalities, we can show this. First is that K5 is not planar. So why can we conclude that K5 is not planar? So K5 is complete graph on 5 vertices. For what? So what is the number of edges in K5? What is, first of all, what is the number of vertices in K5?
N minus 1 upon 2.
Yes. So number of vertices is 5. Number of edges is n into n minus 1. Number of edges is n minus 1 upon 2,
Upon 2.
which
That
is
is 10.
10.
10.
So if we
10 is
look this, then 10. So we have one
15
side
minus
10
2.
10, and this
10.
is 15 minus 6 9. So 10 is
9.
greater than this. So 2 is not satisfied. But we have that for planar graph, this should be satisfied. So since we have this thing, we can conclude that K5 is not planar. Also, why K33 is not planar? So first of all, what are the number of vertices in K33?
6, ma'am.
6, yes. And what are the number of edges?
9.
Yes. So
9.
9.
because in KMN we have 9 edges. So now if we look at the second inequality, so we are getting that 9 is less than equal to 6 3s are 18 minus 6 12. So second thing is satisfied. From second we cannot conclude. So then how can we say that K33 is not planar? We cannot use second.
So you have to use 3.
We have to use
They
3.
are no triangle.
So why
K33 are no triangle.
why
It is
K
bipartite.
why
It is
K33 has,
bipartite graph.
so why
It
a
is a
bipart
bipartite graph. There is no odd cycle, no?
yes, a bipartite graph cannot have any odd cycles.
Odd cycle.
So we know that for bipartite graph we can even say that this that number of edges should always be less than equal to 2v minus 4.
2v minus 4.
So now if we look at 9 and this is 2v minus 4 is 8. So since the second thing is clear, so we can say that K33 is not planar. So we see that K5 and K33 are two examples of non-planar graph. But the interesting thing is that using this we also have a nice characterization of planar graph. So we know that K5 and K33 is not planar, but we can say something more, that G is planar if and only if does not contain a subgraph which is edge contractible to K5 or K33. So if G is a planar graph, any subgraph of a planar graph any subgraph of planar graph will also be planar. So if G contains a subgraph which is edge contractible to K5 or K33, we know that it cannot be we know it cannot be planar. But the interesting thing is that it is a necessary and sufficient condition. So I guess I hope you know by edge contractibility we means that, so if we have some graph like this, if we have this graph like this, E1 is some edge. So by edge contractibility we mean that we are contracting this edge E1. So if this was the original graph, so now V1 and V2 will become same vertex. V1 and V2 will become the same vertex. So all the edges which were going from V1 and V2 now will go from V1. So this is what, so this edge is contracted. So by edge contraction we mean this. So after contracting E1 we'll have graph like this. This is not there, V3. Yeah, so we have V4 and we also have V5. So this is the edge contractibility. So now we are saying that G is planar if and only if G does not contain a subgraph which is edge contractible to K5 or K33. Okay, so now let's first do some questions on planar graph. So
Ma'am, once again, please
yeah,
please explain that it's contractible, ma'am.
explain the okay, so edge contractibility is this. So if you have some graph, suppose if we have some graph like this, suppose, and I want, so these are my edges e1, e2, and I'm not naming other ones, v3, v4, v5. So if I want to contract my edge e1, so basically contracting edge e1 means that v1 and v5 are becoming the same vertex. So all the edges which were going from all the edges which were going from v1 or v5 will now go from v1, and this edge will be contracted, it will become one vertex. So now the new graph will be this. And so there was this edge v1, v3, and there also, okay, so okay,
V4, V2.
yeah, okay, so maybe let's say, so this is by edge contractibility we mean this. Okay, so I'm not so this is giving something weird. So let's say v5 v2, because I don't think we can this, so let's v5 v2, so this is giving us a, oh okay, uh yeah, so this is also giving us a loop, but it's fine, then it's fine, yeah, so it should be this then, yeah, okay. So basically I want, so basically when we are when we are contracting edges, when we are contracting a edge, number of so when we are contracting a edge, number of vertices and number of edges decrease by 1. So all the other edges, so if we are contracting this edge v1 v5, v1 v5, then v1 and v5 will become one vertex, and all the edges that were going from either v1 or v5 will now go from v1 itself. So we see that there was this edge going from v5 to v2 and v1 to v2, so now we'll have two edges. And so in this graph it was like this, and in this example we had this, we were contracting v1 v2. In this example we were contracting v1 v2, and there we saw that there's an edge from v1 to v4 and v2 to v5. So now this will so all the edges which were going from v2 will now go okay, okay, so I'm messing something up, I guess. Wait. If I am this v2 v3, yes, that is fine, yeah, sorry for the confusion, this is fine. So now we see, so we are contracting this edge v1 v2. So now we have this v1 is the vertex, and all the edges that were going from v2, so from v2 we have, there's an edge from v2 to v3 and v2 to v5. Now those edges will go from v1, so we'll have an edge from v1 to v3 and v1 to v5. So when we are contracting an edge, those two vertices become one vertex. So now is it clear? So in this example you see, in this example we contracted v1 and v2. v1 v2 become one vertex, and there were two edges, there were three edges going from v2 to v1, v2 to v5 and v2 to v3. So v2 to v1 edge is contracted, and the other edges are attached to v1 itself. So we have an edge from v1 to v3 and v1 to v5. Now is it fine, the contractibility thing, edge contractibility?
Yes, ma'am. Yes, ma'am.
Okay.
Ma'am, but in the
The-
second diagram,
yes,
we will
yes,
have a self loop, ma'am.
yes, yes. In that second
Uh,
diagram, we'll have a loop. Yeah.
okay, ma'am.
Because this is the thing. Number of edges should only decrease by 1. Number of the edges and number of the vertices should decrease by 1
Okay, ma'am. Okay.
after contraction.
Okay, ma'am.
Okay, so now let's, before doing the colorability thing, let's discuss some examples. So we have seen that K5 is not planar. What about K6 and K7? What do you think? Are they planar? K5 is not planar. Do you think Kn is planar for n great? So basically, we want to see what all complete graphs are planar. So if we look at K1, K1 is just one graph, so it is planar. If we look at K2, K2 is also planar. If we look at K3, K3 is also planar. And K4 we have seen is also planar. All of them are planar. And we know that K5 is not planar. But what about higher ends? Are they planar?
No,
Why? You are right that Kn is not planar, but why it is not planar? Planar
I
for
think
n
I
great.
think
Yeah.
I think Kn where n greater than or equal to 6 contains a subgraph as K5,
Yes. Yeah. Yes.
and that's why.
Yes. Yeah, yes, you are right. So subgraph of any planar graph is planar, and all the higher complete graphs contain K5. Therefore, we can say that Kn is planar. Subgraph of any planar graph is planar. Therefore, we can say that Kn is planar if and only if n is less than equal to 5. N is less than equal to 4. Okay, so is it clear to everyone, this question? Okay. Okay, now next question is, we have to show that any planar graph has a vertex of degree at most 5. So for planar graph, we have this relation v plus e minus f is equal to 2. Yeah.
Ma'am,
Hmm.
in that Euler's formula, you have said that V minus E plus F
Yes,
equal
sorry,
to
sorry,
2.
sorry, 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 sorry. V minus e plus f equal to 2. Sorry. Yes, you're right. It's alternate. Yeah. Okay. Now we have to show that any planar graph has a vertex of degree at most 5. So what do we mean that if G is a planar graph, that means we can say that there will be at least one vertex which will have degree less than equal to 5. So we have to show this, that any planar graph has at least one vertex which has degree less than equal to 5. So suppose, so we show this by contradiction. Suppose not. So this was one of these, this was also proved in lecture, but this is important. Suppose not, suppose not, suppose no, not. So if we are proving it by contradiction, what do we mean that? So we want to find at least one vertex whose degree will be less than equal to 5. So if we are proving it by contradiction, then we are assuming that each vertex has degree of each vertex is greater than equal to 6. Now if we degree of each vertex is greater than equal to 6, then what is the number of edges? 2E is equal to sigma dV. V belongs to V. So we see that each degree is less. So this is, so we get that 2E, so we get that 2E is greater than equal to 6V. Now if we put this in our Euler condition, we get that so we are getting that 2E is greater than equal to 6V, and so if we put this, so we get that okay, E is greater than equal to 3V. So V minus E plus F is okay. Oh yes, V minus E plus F. So wait, show that any if we have 2E is, oh, so we have that E is greater than equal to 3V, but we have already shown that E should be less than equal to 3V minus 6. This was one of the observations, that E is always less than equal to 3V minus 6, but this is giving us that E is less than equal to 3V minus 6. So both these statements cannot simultaneously hold. Therefore, we get a contradiction. And therefore we have at least one vertex whose degree is less than equal to 5. So from this exercise also we can conclude that Kn is not planar for n greater than equal to n greater than equal to 7, because for yeah, because for planar graph we should have at least one vertex whose degree is less than equal to 5. So from previous exercise we can directly say that K5 is planar, or for some n we can also use this result. So if you have, so basically the importance is, if you have any graph and whose all vertices have degree strictly greater than 5, then you can directly say that graph cannot be planar. Okay. Now next question. So we have these two examples. First of all, this is a cube. So what do you think? Is this cube planar?
Yes.
Yes, ma'am.
Okay. Why? So okay, how can so if you are saying that this is planar, then we should be able to have a isomorphic graph where no two edges are intersecting.
Yes. True.
Yeah. So what is so how so okay. So you are saying it is not planar. So sorry, you are saying it is planar. So can
Planar.
you,
Planar.
yes, so you are saying it's planar. So can you give me a description? How can we do this?
Cube is the cube is isomorphic to K2 cross K2 cross K2, where cross is the Cartesian product, and if we imagine, then it is clearly a planar graph, because
Okay. Yeah. Yeah, that is fine. Or other, okay, so that is, or you can say that, so if you look at this face ABCH, and if I expand this face, say ABCH, and if I basically I have a cube and I am expanding the last face, and then I am pushing it down, so I will have some diagram like this. F, E, G, D. So we see that this graph, so basically we have to look at, we took the lower face, then we expanded, and then we projected, pushed it. So we see that this graph, this cube is isomorphic to this graph, and this graph is clearly non-planar, so we get that this is non-planar. What about K42? Let first of all, let's see if we, so what are the numbers. So we know that for bipartite graph, number of edges should be less than equal to 2v minus 4, because bipartite graph has no triangles. So if we look at this, so what are the number of edges in K4? 2. Number of edges are 8, and number of vertices are 6. So 8 is less than equal to 12 minus 4. So 8 is less than equal to 8. So from this inequality, we cannot conclude whether this graph is planar or not. But what, so we cannot use this. But what do you think? Is it planar or not? K42, is it planar or not?
It is planar.
Okay. How? Like, can you give, so if these are my vertices, can you give me an isomorphic graph using this vertices only to give, where no edges are intersecting? Yes. Any suggestions? Okay. So you see, if we have this like this, so what we can do, A, B, C. So complete bipartite graph, we have two independent cells. So if we take our vertex, so these are the cross intersections that are happening. So if we keep our vertex E at top and F it down, so we see that uh, this is this is uh, this is non-planar, right? This is no, this is planar. We are able to draw, we are able to draw a copy. So this is isomorphic to this. Now using these exact, so is this clear why K42 is not, why K42 is planar? Is it clear?
Yes, ma'am.
Okay, now using these two examples, now we want
Madam,
to
we
see.
just,
Yeah.
madam,
Yes.
that is less than or equal to 2v minus 4.
Yes.
Means it is equal to also, then also it is planar, no? Means here 8 is equal to 8, so it is planar.
No. So see, this is not an
It
if
is
and
less than or equal to 8, no?
this is not an if and only if condition. So basically, so we you can use this to show non-planarity, but we cannot use to show this planarity. So this say,
Okay.
so we have that, we, the statement is that if G is planar, if G is planar and has no triangles,
Hmm.
then E should be less than equal to 2v minus 4. But it is not the other way around, that if G is a graph with no triangles and E is less than equal to 2V minus 4, then G should be planar. It is just
Okay.
one way condition. So from this we cannot conclude that it is a planar graph from this inequality. Okay.
Hmm.
Now what about K and 2? What do you think? Is K and 2 planar? Is K and 2 planar? So K and 2 is also like this. V1, V2 and some Vn and two vertices here, W1, W2. So if we want to generalize this, is K and 2 planar?
Yes.
Yes. Why? So why
We
is K?
can we can take the vertices up to one above and one below.
Yes, yes,
W1 and W2 above and below,
yes. Like previously, we can do this.
like previously.
Yes. So we see that K and 2 is planar. Now can we say, now if we have K, M, N. So we see that if M is less than equal to 2 or N is less than equal to 2, then we have, and K N1 is clearly planar. So K N1 is just this. So it is clearly planar. So from the previous example, we see that if M is less than equal to, if either of two numbers is less than equal to 2, then it is planar. So what are the cases remaining? When both M and N are greater than equal to 3. So what do you think? Will this, if, what about KMN when M is greater than equal to 3 and N is greater than equal to 3? Is it planar?
No, man.
Why?
K33 is not a planar.
Yes, K33 is not a planar. What about the rest of the, so if M equal to 3 and N equal to 3. So now
Yeah.
we know that K, but what about the rest of the cases? So so we want to completely classify, we want to among the complete bipartite graph, we want to completely tell what if we have given KMN, which one is planar or which one is not. So we have seen that if M is less than equal to 2 or N is less than equal to 2, it is coming out to be planar. And we have that K33 is not planar. But what about K34? Say, what about K34? Is K34 planar? We have a characterization that uh, G is a planar graph if and only if it does not contain any subgraph that is either edge contractible to K33 or K5. So if, so can we say that if KMN, if M is greater than equal to 3 and N is greater than equal to 3, K33 will be a subgraph of this, isn't it? So if M is greater than equal to 3 and N is greater than equal to 3, won't K33 will be a subgraph of this? And since K33 will be a subgraph of this, we can claim, we can say that KMN is not planar. Not planar for M greater than equal to 3 or N and N greater than equal to 3. So we see that for complete bipartite graph, for complete bipartite graph KMN, it complete bipartite graph will be planar if and only if either M is less than equal to 2 or N is less than equal to 2. If both of them if both of them are greater than equal to 3, if both m and n are greater than equal to 3, then that complete bipartite graph won't be planar. So is this clear to everyone? Since subgraph, since kmn, when m is greater than equal to 3, n is greater than equal to 3, contains a non-planar graph. So if kmn was a planar graph, every subgraph of a planar graph is also a planar graph. But kmn in these cases are containing a non-planar graph, so they cannot be planar. Subgraph. So is this clear to everybody? For complete bipartite graphs, when a complete bipartite graph is planar and when it is not.
Yes, ma'am.
Okay. Now, this was what from your practice problem. So what do you think? Is this planar?
No, ma'am.
Okay, this is not planar. You are saying why?
The edges will be intersecting if we want to, like, if we want to trace it again. The edges will be intersecting. We
Yes,
cannot write it on the like.
yes, but why cannot? So why? But we have to show that we cannot have. So if we are saying that it is non-planar, we have to guarantee that we cannot be we cannot have any
Isomorphic
isomorphic
structure.
structure
Yes.
in which it is not intersecting. So this particular structure is intersecting, but why no other? So if you are saying it is non-planar, so we have this characterization that G is planar if and only if G has a subgraph, if G has a subgraph which can be if G is planar if and only if G does not have a subgraph which is edge contractible to edge contractible to K5 or K33. So if we are so your answer is correct. This graph is not planar. So we can show that this graph is not planar if we can show by contracting some edges, we can have K5 or K33 in it. If we are able to do so, then we can say so then it is proof that this graph is not planar. So in this example you can see, so let's first